Hello everybody and welcome to the NPTEL online certification course on semiconductor devices for the next generation FET, a physics perspective. This is lecture number 5 where we will start from where we left in lecture number 4, and primarily we will be looking in this lecture MOS as a 3 terminal device, look into a formal verification of the threshold voltage, and then we will next subsequently go to uh, two terminal device as a capacitor, right, and how the capacitance will behave when you operate the device in accumulation, inversion and depletion. So, with this short introduction, let me start today's lecture, and let us see. So, let me introduce to you the 3 terminal MOS structure. Now, as you can see here, till now we were all discussing it to be as a 2 terminal, where you put basically the metal gate and the body. The body here on the right, on the left hand side, if you see on the figure, the gate is basically the metal gate which I was talking about. This is the metal gate, right. This is the oxide layer, right. This is the semiconductor, and at the bottommost layer where you have this light green color is basically your body or substrate. And till now we were actually applying a gate to body bias and trying to figure out how the charges near the silicon dioxide interface would change with application of a reverse bias, a zero bias, a small forward bias and a large forward bias. We saw that if it is a reversed biased, then you will have an accumulation. At 0 it will be flat band. As you make your gate voltage slightly higher, you enter into the depletion region, and very large value of gate voltage you enter into inversion region. So, I will talk about inversion in my subsequent slides, but let us see what we have added here. We have added an extra N plus region here, right. This is highly doped N plus region which you see on the left hand side, blue colored, and this let me name it as C terminal, terminal number C, and it is heavily doped. And as you can see, this is basically a self aligned structure, which means that wherever the oxide stops your this this layer, let me as usual, this is source actually. So, wherever the oxide layer stops, that is where your source terminal starts, right, and therefore, these are aligned in the nature. This is not overlap, otherwise in reality what will happen is, this is the oxide layer, generally the N plus layer will start like this. This is my overlap region, right, this is my overlap region. Similarly, the drain will start from here, N plus region. This is my overlap. This overlap gives you C overlap and overlap capacitance. But at this stage, let us assume that there is no overlap and they are perfectly aligned with respect to each other, and we have added an extra terminal there known as C. With this knowledge, if you can see, these inversion layer is already formed. So, you have these negative charges being formed near the silicon dioxide interface, right. You are into the inversion layer, and there is a depletion layer here. But you see, what interesting thing has happened now is, if you concentrate at this particular part, this is nothing but N plus P layer, right. So, there will be always a depletion layer available within N plus P layer, right. This will be always there because it is a p-n junction diode, and the thickness of the depletion layer will be more towards the p side, right. So, when you actually do not give, even if you do not give any external bias, this N plus P junction will be actually giving you a depletion region which will be more towards the p side, and that is what I have drawn here. If you see, this is the depletion region I am talking about. This depletion region is coming by virtue of the gate voltage which you have applied, which we have already discussed in our previous discussions. So, you see, what thing we learn when you introduce a third terminal here known as a source terminal is that you have been able to actually formulate a depletion region even below the source region, which is depleted of any free charge carriers. There are only immobile charge carriers available there. Now, what I do, look at the, now let us look and throw back on the right hand side, which is this graph, this schematic. In this schematic, I have applied a bias on the source side, which is with respect to, of course, the body, which is more than equal to the 0, right. So, when you apply a bias which is more than equal to 0, you actually do what? You actually reverse bias this n plus p junction, because on the n side you are putting a positive bias and the p side you are putting a negative bias. This implies that the depletion thickness on this side, I do not want to name it as source and drain at this stage, on this terminal, at least just below this terminal, the depletion thickness will be growing larger and larger, right. So, higher the value of VCB, which is this one, more will be the depletion thickness, because it is a reversed biased PN junction sort of a element which you can see here. And there will be very small current between N plus and P, again reversed bias because of the minority current carriers. At this stage we will assume that this is infinitesimally small, right. So, it is infinitesimally small, whatever contribution is coming is just because you have a depletion region available there, and there will be also an inversion layer which is available here. So, this I have still not introduced the next terminal, which is on this side, on the right hand side, this side, but this will give you an idea that as you therefore increase the bias, you will obviously the depletion thickness will grow. But please understand, once you increase the bias on the C with respect to B, you are also and let us suppose this side is grounded, let us suppose, then you are also introduce an electric field in the longitudinal direction, right, like this, and you can pull the charge carriers which is available here, right. These are all n type charge carriers, so they will be forming here, they will go easily if you apply a positive gate bias, and that is basically the current which you see. So, this is the basic introduction of a 3 terminal MOS device, right. Let me come to the concept here. Remember, in my previous all discussions, I told you what is the concept of inversion was that when the number of electrons, so if you start with a p type substrate and say there were 10 number of holes available per unit volume near the silicon dioxide interface, right, and if you go on giving a gate voltage such that you are able to form the depletion and then inversion, we say that the onset of inversion will take place when you have as many number of electrons as there were initially the number of holes. That is when you say that your channel is actually being inverted, right. So, you will form a depletion and then you will form an inversion, and that can happen when your surface charges are more than the intrinsic carrier concentration near the silicon dioxide interface, right. N surface is basically the electron concentration at the surface. Which surface? Silicon dioxide surface. All these discussions are with the fact that typically there are no traps available in the silicon dioxide. There are no impurities available there. The surface is perfectly clean at this stage, and we just say that therefore, the electrons which are getting accumulated near the silicon dioxide interface are primarily because of the electric field in the transverse direction, which allows the electrons to flow there. Therefore, we write down N surface to be this formula here, where Na is the doping concentration of the p type by which you dope it, psi s is the surface potential. Remember 2 phi f, why is it 2 phi f now? Remember 2 phi f was that this was the minimum amount of bending of the intrinsic Fermi level, so that your inversion is there. I will discuss this point in the subsequent blank slides, but understand this point, that as you go on applying the gate bias, the intrinsic Fermi level will start going down, right, and it becomes lower than the Fermi level by as much it was higher, will entail that a inversion layer is formed, and that is the reason you see we have added a term 2 phi f here. What is VCB? It is between C and bulk, right, between C and bulk you apply a voltage. Why are you adding this 2 phi f and VCB? The reason being that the reason you are adding VCB in at least in this case is that once your VCB becomes larger and larger, right, you are actually doing what? You are actually increasing the depletion width. I discussed with you in the previous slide. Once you do that, your inversion layer goes down, and that is the reason you see it is psi s minus 2 phi f plus VCB. So, when this term VCB goes up, this quantity goes up. When this quantity goes up, this quantity goes down, right? This quantity goes down, and therefore exponential to that quantity which I have written here will actually go down, and this is true also. Physics, from first principles of physics, this is true also, that as the VCB value goes on increasing, if positive in a positive sense, you do have n surface going down. So therefore, as my VCB goes up, my n surface goes down. The number of charge carriers, inverse charge carrier goes down drastically, right. So this is sort of a way. Now, but let me frame a question for you, think about it. If VCB would have been negative, then what would have been the case? The case would have been that you are actually forward biasing this n plus p layer, this one n plus p layer, and when you are forward biasing, there will be no depletion region. When there is no depletion region, it will not eat away into the inversion layer here. You got the point? And that is the problem. So if you look, if you let me rub this ink and show it to you. So if this is n, so this is p, right, this is p, this is n plus. So the depletion region is actually also hitting this part also, and that is where it is eating away into the inversion layer. So your surface charge density is falling down. So more you try to increase the value of C with respect to B, your surface charge density goes down, inverse of surface charge density goes down, and therefore you have to apply a larger gate voltage in order to sustain a channel. You are able to get the picture, and therefore the threshold voltage goes up. Therefore, with this basic sort of principle available to you, we can look at this fact that VGB, gate to bulk voltage or gate to bulk, will be VFB plus psi s, we have already seen, plus this term which you see, this term, right. This term which you see will come into picture, and there will be a gamma. This is known as body factor. We will not go into details at this stage, but this is a body factor, right. This is a body factor, and obviously very straightforward and simple. If you increase the VGB, VGB will increase. If you increase your psi s because of some problem, VGB will increase. If this whole quantity increases, obviously your VGB will increase. You got the idea, and that is the reason why if you see, for example, the surface potentials comes from the fact that how much amount of potential is available at silicon dioxide interface. If you go on increasing the gate bias, obviously your psi s will go on increasing. So if you increase this quantity here, obviously this quantity will, this is almost constant, this quantity will increase, right. This quantity, when this quantity increases, this quantity also goes up, psi s also goes up, right, and so on and so forth. So this is a basic fundamental principle of the of formation of an inversion layer, basic inversion fundamental. Let me come to now a detailed study of the threshold voltage from the band diagram as perspective of it, and then I will try to give you the value of the threshold voltage in terms of total charges. So let us suppose I have a MOS layer, right. I have a MOS layer here. This is my metal and oxide layer. This is my oxide, this is my metal, and this is a semiconductor which is basically p type initially. So let us say I have this valence band here, EV, right. I have also a Fermi level which is close to EV, let us suppose. So it is a p type semiconductor, and then I have an intrinsic Fermi level, right. This is EFI, and then I have a conduction band here. This is my conduction band. This is the conduction band. This is a flat band condition, so there is no bending of the bands taking place on the semiconductor side. This difference between EFI and EF is basically equals to Q times phi of FP, right. What does it tell me? This Q phi of FP tells me how much the device is basically p type. That is also one of the reasons EF is very close to EV. So if you see, if EF is very close to EV, EFI minus EF will be typically a large quantity, and which means that it is more of a p type, right. So that is the reason this Q times phi FP gives you a sort of a qualitative as well as quantitative analysis of how far the substrate which you have taken is p type, right. And this is no, I have not applied any bias here. So now if I apply a bias here which is positive in nature, what will happen is this thing will happen. So let me draw it in inversion. This so let me draw a line here, and then what will happen, this conduction band edge will start going down, this will go down, and this will also go down. So all these three, EC, EFI and EV, they will all go down by how much, by the amount of potential of applied here into Q, right. So, if you have applied V, then you multiply this with Q, all will fall by that factor in the reverse direction, because it is minus Q into V which you will see. Now, we define and the potential at this particular point at the silicon dioxide interface is referred to as psi s, the surface potential. Now, we define that we will have threshold voltage, right. We will have threshold voltage when your psi s becomes equals to twice phi of f p, means. So, this is one f p and this is another f p. So, this is your phi f p and this is also your phi f p. You got the idea? So, it has dropped by the same factor as you increase the voltage. So, I get 2 phi f p, right. When you, if this is for a p type semiconductor, if you have an n type semiconductor, p type. If you have an n type semiconductor, then psi s must be equals to 2 phi f n for an n type semiconductor. With this knowledge or with this basic idea, let us see how the charges will behave once you apply a positive bias, right, on the metal side. So, when you apply on the metal side a positive bias, let me plot for you the metal oxide semiconductor charge distribution and show it to you. So, this is my metal layer, this is my oxide layer. So, this is the interface, silicon dioxide interface. This whole thing is oxide, this whole thing is oxide, the whole part is oxide. So, when you apply a metal, you will get on the metal side a value known as QMT prime, which is the charge per unit area in the metal, right. QMT prime is the charge per unit area in the metal. This will entail a charge on the oxide side, which is QSS prime, charge per unit area, right. This consists of many factors I have already discussed in the class. For example, it is consists of fixed charges, mobile charges, immobile charges, impurities and so on, traps and so on and so forth. So, that is QSS. In order to balance these two, what happens is that on the P side, which is on the P substrate, on the semiconductor P type substrate, you have this charge. This is x dt. X dt is basically the length of the depletion layer. You will have a charge which is equals to QSD, right, depletion prime. This will give you the maximum value, and this will be equals to Q times you will have NA, right, into x dt, right. This is the total charge which you will see, and this charge has to be balanced across the network, right. Why? Because it is Q time. Why it is Q times NA? X dt is the thickness of the depletion region. I will show you what does that mean. Basically, this region, this is x dt. So, if you multiply that with Na into Q, you get the total charge in that particular region, and you can see it is much large. So, it is relatively much larger, right, as compared to among the metal on the semiconductor side. It is in fact, if not larger, it is actually extending more towards the semiconductor, whereas in the metal and oxide they are very near to the metal layer and very near to the oxide layer. With this fundamental principle, or with this, let me write down the expression now. So, this will be Q of MT prime plus QSS prime must be equals to Q of SD maximum, which you can get prime mod of it. I am not worried at this stage about the sign of this. So, I get the metal charge plus the oxide charge must be equals to the QSD charge, right. So, if you take it and find out, we know that Vg, right, will be equals to change in Vg will be given by V. So, change in Vg will be change of V oxide plus change of phi s, psi s. Now, you can write down this to be as Vox, right, voltage across the oxide layer plus surface potential plus phi ms. We have already discussed this point in the initial stages, that it is the voltage drop across the oxide layer, surface potential at silicon dioxide interface, and the metal semiconductor work function difference, which you see comes out to be equals to VGS here. Now, at threshold, let me write down what will happen at threshold. So, at threshold, let me write down for you. What happens is that I write down VGS or VGS to be equals to VTN, the threshold voltage will be equals to VOX at threshold plus 2 times phi FP by the condition, which condition, this condition, psi S should be equals to 2 pi FP plus phi MS. And if you look at VOX at threshold will be given as Q of MT prime divided by COX prime. Fine. So, VOXT is equals to QMT prime by COX prime. Now, this can be written as this QMT prime by COX prime can be written as 1 by COX prime, right, into QMT can be written as this could be written as this quantity minus QSS prime. So, I can write down this to be as QSD prime max, right, minus QSS prime. So, if you divide by C oxide on both the sides, I can get, therefore, I can write down, let me write down the value of VTN now, right. Let me divide into 3 parts. So, my VTN value which I have taken from here will be VOXT. VOXT can be written as QSD prime max, right, prime max divided by COX prime, right, minus QSS prime divided by COX prime plus phi MS plus 2 phi FP. And therefore, this can be now C oxide can be taken together and C ox is equals to T ox by C ox by epsilon ox. Remember the value of C ox prime which is charge per unit area is basically capacitance per unit area is you have to divide it by area. So, what you get from here is you get VTN to be equals to QSD prime max QSD prime minus QSS prime blank, right, into T ox by C ox T ox by epsilon ox. Why? Because it is divided by C ox prime. C ox is equals to epsilon ox by T ox. So, when you divide it, it becomes T ox by epsilon ox. This plus phi MS plus 2 phi FP. The same thing will again come into picture. Now, we already know that VFB is equals to phi MS, right, minus Q prime by C ox prime. We have already studied this particular problem and therefore, the final expression for VT, let me write down for you, that is very important, is VTN will be equals to QSD max prime divided by C ox prime plus VFB plus 2 phi FP. This happens to be your final threshold voltage value. What does it tell me? That the threshold voltage depends upon 2 phi FP, it depends upon VFB, it also depends upon the maximum depletion charge which you are storing at the MOS device and also on the capacitor, right. And so, you can see very easily here, not doing anything, that if you actually if you increase the value of COX, right, your VTN goes down. That means, if your COX actually goes on increasing, right, COX prime goes on increasing, your VTN actually starts to go down, right. Now, how can you make your COX go high, and why is it so physically true? Because if COX prime goes high, you are actually storing larger amount of charge for the same amount of gate voltage, right. So, I need to give a lesser amount of gate voltage to invert. You got the idea, and that is the reason I say COX prime increase, but let us correlate this with the physical parameter. COX prime increases, COX prime is epsilon ox by T ox, right. Now, this will only increase when T ox prime actually reduces, because epsilon ox is almost constant. So, this reduces, which means that when T ox actually reduces or the oxide thickness goes on reducing, you are trying to bring the gate closer to the channel, and therefore, you have a better control over the channel, and that is the reason your threshold voltage actually shows a drop or shows a decrement in the value. So, this is one very fundamental first principle sort of way to design low threshold voltage devices. With this knowledge, if I therefore plot on the x axis and y axis, on the x axis I do a doping, right, and this is an A doping, acceptor ion doping, and on the y axis we are trying to plot the value of VTH. The typical way of looking at it is something, it is something like this, it goes like this, right, it is something like this, and it suddenly increases. And it suddenly increases, why? Because for low values of acceptor ion concentration, right, your depletion region charge is relatively very small, and therefore threshold voltage is small. But as the doping goes on increasing, that factor on the left hand side becomes higher and higher, and because of which the threshold voltage suddenly shoots up to a very large value when your doping basically increases from a low value to a high value. This is the doping of the substrate here, right, not of the channel or channel region or the any other region. This is, I have told you a brief idea about the threshold voltage, how to model threshold voltage and what are the principles of modeling the threshold voltage. Let me end this discussion with one small numerical example to showcase this. Say I have a two terminal device where I have n substrate, right. So, it is basically a PMOS. I have an M substrate available there whose TOX value is 120 angstrom, right, and QSS, which is the oxide charge density, is 2 into 10 to the power 10 per centimeter square, and my threshold voltage, the question which I am giving it to you is that I want to design a threshold voltage such that the value is equal to 0.03 volts approximately. How will you design it? That is the question. So, I have been given a P type MOSFET with obviously an N type substrate, TOX is already given to you. I know the value of QSS prime, you are told to get the value of VT, with threshold voltage of the design. So, and let us assume that I take a P plus polygate at the MOS, right. Now, in the P plus polygate MOS, let us consider ND is also to be equal to 10 to the power 17 per centimeter cube, and phi ms, let us assume that for a P plus polygate my phi ms value is 0.1, these all will be given to you 1.1 volts approximately. So, what I get from here is that the phi fp is nothing but kT by q ln of Na by Ni, right, and this comes out to be 0.0407 volts, right. This is phi fp, which is the difference between what EFI and EF. The difference between them is 0.047. So, this has to be, so when this goes to 0.814, which is twice the value of phi fp, then only I get an inversion, right. So, this is you get EFI minus EFP as the value here, right. So, now I need to find out the value of XDT. XDT is the thickness of the depletion layer, and this comes from the PN junction diode theory, that this will be phi Fn divided by Q times Nd to the power half. And if you put the values, I will get 1.026 into 10 to the power minus 8 centimeter. Once you know the value of XDT, you can now extract the value of QSD prime max, right, and this comes out to be what, Q XDT, right, into Na or Nd in this case, and if you solve it, I will get 1.642 into 10 to the power minus 7 coulomb per centimeter square. Now, what I am supposed to do, take these values, put into the expression of VTP, threshold voltage. So, let me put it in the threshold voltage expression, and I will get VTP to be equals to minus of QSD prime max. Please understand, I have put a minus sign, and understand the reason why is it minus, because it is not a P type, it is a P type MOSFET. So, it will be always negative in nature, right, for this to be true, minus QSS prime, right, minus into Tox by epsilon ox, right, plus phi ms plus 2 phi fp. If you put all these values have been calculated, and if you put all these values, I will get VTP to be approximately equals to minus 0.296 equal to 0.296 which can be approximated as minus 0.3 volts, right. So, what I have shown you in the small numerical here is how can you design specific threshold voltage device, right, from the notations or from the input values. As far as phi ms is concerned and nd is concerned, it will be given to you by the designer. So, you need to find out the value of VTP in this manner, right. So, with this let me end today's lecture, and then we will start the next lecture subsequently. Thank you.